In this next section, we have a look at the energy or heat which is released or absorbed during chemical reactions. While we're doing this, we come across two different types of reactions. One is a reaction which absorbs heat from the surroundings as the reaction occurs, and they are called endothermic reactions. Because the energy is being absorbed from the surroundings, what we notice in those cases is that the temperature of the surroundings decreases. So we would feel that as it getting colder. The other type of reaction is one which releases heat energy to the surroundings. And these types of reactions are called exothermic reactions. In these situations, what we notice is that the temperature of the surroundings is going to increase as that heat energy is released. And we're able to actually calculate the heat of a reaction based on the quantities of substance which is reacting. So we can either use some pre-known knowledge to calculate how much heat energy we expect to be released or absorbed, or we can record data about how much heat energy is actually released or absorbed. When we're talking about the heat of reaction, we're talking about the quantity of heat that is released or absorbed when specific amount of substances are reacted. Now, if this reaction occurs at constant pressure, it is referred to as enthalpy change, which has the symbol of delta H. The delta representing change and our H, of course, leading back to our heat of reaction. Now, the units of enthalpy change are kilojoules per mole. Now, there may be times when you need to convert that into kilojoules per gram, and the way that you do that is by dividing by the molar mass. So if we have a look at what actually happens when we do that, if we've got kilojoules per mole, now molar mass has units of grams per mole, so if we divide kilojoules per mole by grams per mole, we can see that the moles cancel out and we're left with kilojoules per gram. Another term that you'll come across is the molar enthalpy change, and the molar enthalpy change is the amount of heat released or absorbed when 1 mole of the reactant reacts. All of our chemicals, regardless if they're our reactants or products, have a certain amount of heat or energy stored within them. Now, depending on whether the reactants or the products are higher or lower in energy determines on whether we have an endothermic or exothermic reaction. So, for example, let's have a look at this case where our reactants have this particular amount of energy and the product that is going to be produced has this amount of energy, so we can see it's much lower. Now, as the reaction proceeds, we start with our reactants. We need a little bit of energy to get the reaction going, but then overall our products are lower in energy. So what we see happens is the difference between the energy of our reactants and our products is this here. And this is what we refer to as delta H, for our enthalpy change. This little bump here, the amount of energy there to get the reaction going, is our energy of activation, or our activation energy for the reaction. Now, the other situation that we can have is where our products of the reaction are higher in energy than the reactants. So in that case, we need a certain amount of energy to get the reaction going, and then our products have higher energy. So if we have a look at this situation, the difference in energy between our reactants and our products is again delta H. And the difference between our reactants and what's required to make the reaction occur is again our activation energy. So if we have a look at this first situation on the left here, our reactants have more energy than our products. So that difference in energy that is no longer required in our products because they're lower needs to go somewhere, and that's why it's released to the surroundings. So this is what happens in an exothermic reaction. If we have a look at the diagram on the right here, we notice that to go from our reactants to our products, we need an input of energy because the products are higher in energy, and that's what's occurring in an endothermic reaction, and it's why the heat energy is absorbed from the surroundings because additional energy is required for those products. So essentially, the enthalpy change, which we've looked at above as delta H, is equal to the heat stored in the products subtract the heat stored in the reactants. So if we have a look in this situation for our exothermic reaction, the heat of the products is less than the heat of the reactants. Because of that, delta H is going to be negative because we're subtracting the largest number from the smallest number, which is why we end up with a negative outcome. So that's why delta H for exothermic reactions is negative. If we have a look at the endothermic reaction here, we notice that the heat stored in the products is greater than the heat in the reactants. Oops. What that means is the change in enthalpy in this case is positive because we're going to have the smaller number subtracted from the larger number. So H is positive. So that's why the enthalpy change for endothermic reactions is a positive value. Now you can use the molar enthalpy change to predict how much heat energy will be released or absorbed in a specific reaction. We use a lowercase q to represent the heat energy released or absorbed. And that value is going to depend on the molar enthalpy of the reaction, as well as the amount of the specific substance used. So what that means is that these two pieces of data, the number of moles being reacted and the molar enthalpy, need to be for the same substance. In the next video, we'll have a look at some of the important equations that you'll be using when you are measuring energy changes.